All right, so my point was to use this microphone to record. So we'll see how it goes. I will look, like a complete clown with two microphones. You'll have to, deal with it. Is it okay? Sorry about that. No, that's how this class is going to go. All right, without further ado, let us go into the class. We can see the slides. Okay, great. Yeah, go, of course. Yeah, because I didn't try to provide Zoom link yet, because as of last class, I didn't even have workable audio. So if this works today, maybe next time we'll have a Zoom link. But so far, remember, we have, how would I put it? It's like offline class. I'm technically unable so far to give hybrid education. I would have liked to, but you see how it works. Like this is a hybrid education that I get. So, if someone of you, by the way, have a solution for how I can do it perfectly, let me know. I will be very grateful. All right, let us start. So let us remember where we were last time. So last time we went to discuss transfer functions. And you remember what the story about transfer functions was. The story was that you have a, how should I put it? You have a function that has input and an output, right? That is the first time that we saw this idea of u as a input, right? And you saw that in transfer functions, it didn't make any sense to discuss it without u as input, right? Let me just show. By the way, sorry for everyone who listens online. The audio quality is going to go down when I put the microphone down, but hopefully it still be heard. Right. So last time, what we saw was that if I even have markers. So many technologies. So last time what we saw was, for example, for such a system, it makes perfect sense to write it, let's say, in this form. Of course, you remember the submission notation, right? And then we brought it, as a. So basically, it made perfect sense to write it as a transfer function, right? And that was completely based on the idea that there is some input and there is some output. Okay, good. That is great, but the problem with that is we don't really know what this input does. If the system was homogeneous, so let's say the way we put it on the slide, system number one, it is x dot equal to x. This system is homogeneous. We can actually talk about its stability. We can solve it forward. We know how to deal with it, right? For example, system one is unstable. Am I correct? Is it unstable or is it stable? Unstable? How do you know? Sorry? The solution will diverge, but how do you know? Intuition. Can you calculate? Come again?
Maybe we can use the final criterion here.
What is the criteria for stability? Criteria. Yeah, real parts of the eigenvalues should be less than or equal to 0, right? What is the eigenvalue of system number one? 2? How do you know? Yeah, eigenvalue of a 1 by 1 matrix is the only value it has, right? Yeah, great. Is exactly. If you disagree with that, you can remember it two ways. First, definition of eigenvalues. where eigenvalue is such a value that you multiply a vector by your matrix. It is equal to some value multiplied by a vector. Of course, if your matrix is 1 by 1, that value is itself eigenvalue. In a different way is diagonalization. If your matrix is diagonal, all values on the diagonal are eigenvalues, correct? So that means that for a 1 by 1 matrix, it is diagonal matrix. Its value on the diagonal is eigenvalue. Okay, so if I give you example with a diagonal matrix, you should know the eigenvalues are elements of the diagonal. Okay, great. So it is stable, unstable for system number 1. Since system number 2 though, that one is has an input. So that's exactly what we studied last class. It has input. We can write transfer function for it. Can someone tell me if it is stable or unstable? Yeah. Good. That's exactly the correct question, the correct answer. Give me U and then I can tell you if it is stable or unstable. So far, it is anyone's guess, right? Good. So let me choose U the way I chose it here. First, I will choose 0, and I get exactly the same answer as before, right? If I choose 0, then the system is unstable, correct? Good. Then I can choose -3. If I choose -3, what will happen? What will happen? It will become stable. How? Eigenvalues will be -1, right? Yeah, in this exact sense. So what? How do we choose U in this case to make system stable? Can you give me more concrete answer? What is my process of choosing the U in this case? I mean, intuitively, to make sure that the system is stable. I mean, for this system, you can just choose U equal to X such that equals to AX, such that A is what? Less than -2, right? Then it will be stable. If you choose U something else like a sine T, will it be stable or unstable? Unstable. How do you know? First you? No, you had an answer, right? Sorry. This is difficult. This is because of the masks. Yeah, sorry. So your point is, if you get like sine of T, it doesn't actually change the stability of the system. Yeah, exactly. And if you think about it, it is called particular solution, right? For a differential equation. I'm not sure if you remember it from your course on differential equations, but it is called a particular solution. Particular solution does not influence stability of the system. Basically, just influences steady state behavior. And in this case, the system doesn't have any steady state because transient process is going to infinity. So if you basically the way, let me illustrate it this way, just for refreshment on differential equations, which is extremely important, by the way. If you see differential equation, it has two parts. One is dependent on x, another dependent on t. You can treat them separately, and you can solve first equation as if there was no t in it. So just treat the, in this case, x dot equal to 2x. And you get a general solution. It's called fundamental family of solutions, basically. For every initial condition, you can get a different solution, and those solutions will provide a basis if your initial conditions are independent. Don't sweat it if it sounds like a huge lot of mathematics, but it's not. It's just you solve for, let's say, 1 0 0 0, then 0 1 0 0 0, etc. Right? For example, you get family of solutions. That family tells you a lot about transient process, right? It's how your initial conditions converge or diverge. Okay. And then you have a particular solution, which you have to solve the whole equation for, but gives you one solution, not a family of solutions. And that one solution is what is going to determine long-term behavior. So if you are interested in how your transient process is going, for example, how fast it goes to 0, just ignore sine t, etc. Ignore parts that depends on t entirely. If you are interested in long-term behavior, solve the whole thing together. So that is but get only one solution. You don't have a family of solutions. You don't care about initial conditions, basically. So that is an interesting way to analyze differential equations. But anyway, so if I put sine t there, I'm not affecting stability. If I put minus sine t, I'm not affecting stability. If I put, for example, 20 there, I'm not affecting stability. I'm not sure what will happen if we put, for example, t there, just t. That would be interesting to think about, right? You can think about it on your own. I'm not going to ponder this topic, but because it have no practical use for us in this course. But think about it. Would it be stable if I put t there? Or if I put t squared there? Of course, it's not going to be stable right now because it's unstable to x. But if it was minus 2x, would have been stable with t as a u, so with a ramp. Interesting question, but okay, just interesting mathematics to ponder. Right, but I'm going to always choose stuff like x times something, okay? Why? Because often enough what we care about is to stabilize the system. And as you can see, this is the way to stabilize a linear system. You can put x squared there, but it's not going to be linear anymore. So it will be more difficult to analyze. But you can do it. And people actually do put like x squared, x cubed, etc. You find it in the papers on nonlinear control, even for linear systems. So, go ahead, use anything. But linear functions provide you enormous amount of abilities to analyze. That's what I'm going to give you this class. Hope we are going to be on time to cover all of this. So let's go through a definition. So if I give you a dynamical system with the input and I ask you to find such control that this dynamical system, after I put use this control as input, is stable, that is called stabilizing control. So basically, when I ask you to stabilize a system or find a stabilizing control, I'm just asking you to find such u, which when you plug it into your equation, it gets you a stable system. Let me write one example on the blackboard. I'll try to read it out loud for people who only have audio. Today we don't have camera. So let's say it is x dot equals to 7x plus u. It's very trivial. I mean, they're all trivial in sense, linear systems. The only non-trivial part comes from your ability to compute eigenvalues and null space, or SVT in your head. We cannot, usually. And that is the only non-trivial part of linear control. If I could compute stuff like this in my head, we would do like 10 by 10 examples on the blackboard. Would be trivial as well. But anyway, so finally stabilizing control. X dot equal to 7x plus u. What is the stabilizing control here? U equal to what? Minus 7x. That would give me a system which is what? This will give me a system which is x dot equals to minus 7x plus 7x equals to 0. And that is system stable or unstable? Stable is the sense of Lyapunov. Okay. Also people call it marginally stable in some textbooks, but stable in the sense of Lyapunov or just stable or marginally stable. But weighted, it is not a simplicity stable. And when I say stabilizing control, I usually prefer if you give me asymptotic stability. So what do we in the solution? Yeah, let's just 8x. I mean, I understand you want to answer general as possible, but equality is always nicer than inequality because it's easy to plug. That gives me x dot equals to minus x. That is state. Good?
Minus 8. Minus 8.
Minus 8. Important detail. Okay, good. So that is a stabilizing control. By the way, this is not a linear control term. It is just general. Controls that can make you stable, stabilizing control. That is a terminology that comes beyond linear systems. It's just general. Great. Now, let us consider this LTI number 4. That is something that we saw before, right? LTI number 4. That is what we call a state space model, right? Everyone familiar with it, right? So I propose to use linear control, which is, as before, proportional to state. So I just multiply our state by matrix K. And let me plug it in equation number 6. Just plug this guy in, yes? What is the... No. Equations here all state space. If it was transfer function, I would... today, no transfer functions. So number 5 is just equality. So it's not a differential equation, so it cannot be autonomous. Equation number 4 is non-autonomous because it has U. Good. Interesting to ponder about autonomy of the systems. But you'll soon, I mean, you already saw a little bit about it when we saw face portraits, right? Those are features on autonomous systems only. Okay, good. Now, plug in 5 into 4, and you get equation number 6. Do you see that it's like trivial, right? I just put in minus kx instead of u. And I will take x out of the brackets to get 7. Seems so far completely trivial, right? It's not even interesting. It's just, and I just put matrix instead of x, instead of u. It doesn't seem profound at all. It's just a boring linear algebra exercise. But this result actually is not only interesting, it is infinitely useful. So all you need to do now is to find me K matrix such that A minus BK eigenvalues, bless you, would be negative or have negative real parts. So all you need to do is to find such K matrix that A minus BK has negative real parts, eigenvalues for this matrix. I will, for shorthand notation, yes, questions? Other one question. If you allow me, I will call this matrix stable in just for the day maybe, because saying that matrix has a negative eigenvalues of the matrix have negative real parts is like 7 words. So I will just say matrix is stable. Of course, matrices are not stable. The linear systems that they represent are stable, okay? But you'll get what I mean. Because today we are going to discuss this like 12 times at least. So just for today, allow me the liberty. Okay, good. So you can see the equation number 7 gives us already the tools to compute control. How? Well, can you find K that has real negative, that will provide this matrix with negative eigenvalues? Well, not necessarily. Maybe it would be difficult, right? But for 2 by 2 matrix, maybe you will be able to just, just do it by hand. What you can do, for example, if your matrix is bigger, but it is almost negative, is to change one parameter slightly and plot the eigenvalues. and see if the eigenvalues at some point kind of go down to in terms of like real parts, if they go to the left half of the complex plane. That is a graphical way to approach it. There are systematic ways to approach it. The systematic ways are very simple. For example, some software just allows you to directly say that this matrix should be negative, semi-definite, which would mean that it would have negative eigenvalues. Go find me k. And there are software that would do it for you. That is what a semi-definite programming does. That is a type of optimization that if you go to any track where I teach optimal optimization and computational intelligence as a course, we'll study it the whole semester. But basically it boils down to one line in code to solve this problem. But there are many methods. In the labs, you will solve this problem by doing pole placement. And pole placement is just an algorithm. It is, the way you studied sorting algorithms and other stuff. You know that there is some clever person who already invented all the steps. And basically, for this course, we're not going to study how exactly it is done. You just know that it was invented, and you can call this algorithm. It's called pole placement. It gives you exact eigenvalues you want. I think we'll have maybe a little bit of in the exercise, at least reading or something for it, but don't feel bad about not learning, pole placement because there are like thousands of algorithms in this field, and we are going to learn one, which is very useful, but it's not pole placement. So don't worry. The fact that you will use something without learning it is okay, because we are going to instead learn something more useful and something that is more often used in practice. So good. But pole placement for you, it's just a Python import scipy linalog and place, something like this. I'm not sure if it is in scipy or in numpy, but okay, good. So this problem is solvable, and solvable with algorithms and by hand for 2x2 case for sure. Great. Now we kind of know how to find stabilizing control, kinda. Of course, it depends on software or your intuition. So all we need to do is to make sure A minus BK is stable. Great. That is, by the way, this same statement, but outlined. So if it is, if they are by the way, if the eigenvalues of this are, again, non-positive, it is stable in the sense of Lyapunov. And that often happens in practice. Sometimes it is impossible to make a system stable. Yeah, you have a question?
We always have linear dependence between U and X.
So this is called linear control law when they are linearly dependent. And we prefer to have linear control law for linear systems. This class, in just a couple minutes, we'll see affine control law, which will be slightly different. But I think it will be within your expectations. You'll just have a constant term. You can have different style of controls. But for linear systems, you can prove, and that we'll do that in like 5 weeks, that this is optimal. So you cannot do better than this for a certain type of cost functions. We'll just prove that it's best we can. And this is the most common type that's used in practice by far. I mean, if you find a system where you use nonlinear control, as in like that is not based on something like this, you can consider yourself lucky. Even nonlinear control is mostly based on this and some nonlinear operators on top of that. Pretty much all you see in your surroundings, from airplanes to SpaceX rockets would most likely, if not always, have this type of control under the hood. And that is not because, the world is simple or something. It's because everything can be approximated by Taylor series. And first term in Taylor series is linear term. And most processes which don't go crazy are well approximated by the first term locally. And our controllers, etc., allow us to do approximations every microsecond or every millisecond. So you don't have to always consider nonlinear terms. But of course, I'm saying that, but as I said, nonlinear functions on top of this exist. And maybe we'll go to it a little bit at the end of the course. But yes, indeed, this form is so general that, with it, you can do almost everything. Without it, you can do almost nothing. So, good question. Now, let us try to go one step deeper. As just you pointed out, and the slide anticipated your question, we don't have to have this pair to work with. And this pair will always lead you to one and exactly the same solution, stabilized solution. It is zero solution, right? As I said previously, this, let me write it down. So this system can have only one solution unless A is degenerate. And the solution is x of t equal to 0. That is the only stable solution it can have, right? Stable solution. I mean, of course, it can have a lot of other solutions, but they're not going to be stable. So it can have only one node that is x, x equal to 0. That's pretty much what I mean. It can only have one node. This system, autonomous ax equal to ax system. Now, when we go to our x equal to ax plus b, and this use u equal to minus kx, we substitute, we get another system which is autonomous. X dot equals to a minus bk times x. And this system, exactly as the previous one, can have only one and single node. And the node is x star equal to 0. The solution that we can stabilize is x of t equal to 0. That is not interesting. One solution that we can stabilize, not interesting. We want different solutions. We want our airplane, for example, to take more than one trajectory. Okay, and that can be solved by introducing for example, dynamics with a constant term. In this case, c. I apologize about the light. It's probably going to get even worse this time. We're going to think to do something about it. All right, while we still have part of the board. X dot equal to ax plus bu plus c. This is what we call affine system. Affine in algebra means that instead of being linear, it has a constant term as well. If it feels kind of like, why such a grand term for such a obvious thing, please don't look down on affine systems. Not only do they serve enormous purpose, they also a degree of difficulty above linear systems. So please pay respect to affine systems. They deserve it. So this affine system will force us to actually use a controller which should be affine as well. So instead of just being linear with respect to x, it is also going to have a constant term. So it will be minus kx plus u star. I'll insist on using u star for the constant term. And you can start to object. You can say, wait a second, you used star before to declare your nodes, like nodes, or your solution, points where your solution goes to 0, right? X star was a node, right? Well, you will see soon that u star is also part of the node. It is u star also is kind of like, if you think about the system x dot equals to ax plus bu, x star and u star provide a x dot equals to 0 solution. You'll soon see that. Or at least it goes in this direction generally. But don't use it as a rule. Use it as a, what do you call it, heuristic. But anyway, let us think how we can solve this problem. And I really hope, I will write down everything that you cannot see. All right, so the first step we can take is to substitute, obviously. Can we still see what is written on the slides? We can see the formula, right? All right, so I will just hurry up with the slide and then I will draw it on the blackboard. So what I do is I substitute u in our first equation, and we'll get x dot equals to ax minus b kx plus pu star plus c. Okay? Just that. Now, if we choose u star such that b times u star is equal to minus c, we get exactly where we started, right? So we'll get to the equation x dot equal to a minus bk x. Now there comes a question. Is it always possible to find such u star? No, right? Come again? That's not true. Good direction of thought, but it's not true. Exactly, but the opposite is not true, right? To be able to find u star, b doesn't have to be invertible. In fact, in practice, b is never invertible. That is kind of interesting. I mean, in practice, it actually never happens. Except, maybe for some systems that I haven't seen in engineering practice. But there is a good reason. For example, for mechanical systems, B is always block of stuff and block of zeros. It is interesting because it is such a natural thing to assume, right? B should be invertible. But can you or someone else specify what exactly is the condition for this to be solvable? For BU star equal to minus C. There is a condition, algebraic condition, which you can just say. Don't worry, in like 2 weeks or 3 weeks, we will study those conditions exactly, but maybe you remember. Well, I'll tell you for you. Minus C should be in the column space of B, right? So B should be something that that spans the space where C exists. So for example, if C is equal to 1 and 0, one of the columns of B should, or the combination should be able to produce this 1 and 0. Yes? C is a vector. Yeah. We'll use on the slides big letters for matrices, small letters for vectors, and bold for vectors matrices, and not bold for scalars when we can. All right, so now what we solve for the first time is a condition where the control can exist or cannot exist, okay? So what happens is, if your minus C is not spanned by your columns of B, then you cannot solve this problem. That is perfectly normal. Let's say they ask you to hover your quadrotor in this position, right? The fans are going this way and they want to hover. Impossible to hover, right? This problem is going to be expressed in exactly this form, and minus C is not going to be spanned by the B. Maybe you think right now that I'm, simplifying. Right now I'm not simplifying. Hovering of a quadrotor is exactly a linear problem, because you're hovering, you're not moving around, so your nonlinear dynamics is well approximated by its local linearization, because you're not going anywhere. You are hovering, you are on the spot. So you can just write A matrix, B matrix, and C vector for quadrotor. C vector is, by the way, gravity. And you will just solve it exactly this way. You want to hover this position, you also find it is impossible. Why? Well, because your vector of force is going this direction, so you cannot really hover. You need to compensate downwards vector of gravity. The only hovering position is this position, where your vector is entirely compensating your gravity. That's exactly it. That's the span of a B matrix. Good. Now that sounded simple enough, and we already got something out of it. I didn't go into discussion. Let me just, before we go, let me just give one more discussion point. So those types of problems now allow us to have different nodes, right? This guy could only have one node, but let me put make it down. But the guy x dot equals to ax plus c can have any node, right? All you need to do is to solve this equation. A times x star plus c equals to 0. So x star can be given as any vector label. I'm not sure if I'm using notation right now. I don't like doing it on the fly, but any A pseudo inverse times C, anything like this. But that I don't like. I like this better. Why? Well, this is exact condition. This is some sort of iffy stuff. For example, this would also have to include all null space of A. So plus null of A times coefficient, for example. No, because if x is a null space of A, it doesn't actually change anything. So I don't really like this. So let me just keep it back to this original condition. We'll discuss null spaces in a couple of lectures, so don't worry. By the way, that's going to be a contribution for you as a data scientist, if any of you are going to go this profession. But anyway, here is a condition for node. Any x that can make this go to 0 is a node. And in exact same way, in our case, when we discuss a minus bk times x plus c, if you have this c vector, you can use it to achieve any node, not just 0 node, okay? That is what C does for you. It allows you to change nodes. Instead of one node, you can have any node now. Good. Now let us move on. Today, basically, the rest of the lecture, I'm going to give you different aspects of control. And I'm a little bit afraid it's going to be boring. A little bit afraid, because it's also infinitely exciting for me, but maybe not for everyone. But please try to keep your attention to the rest of the class, because it's going to be very useful, and it's like, going to answer pretty much all your questions about controls that you could have. Right. Now, let us consider this following situation. And we cannot see anything on the blackboard, so I will write it. So let's consider the following situation. You have x dot equals to ax plus b, your typical linear control system. And you want to stabilize a solution which is equal to x desired equals to x desired of t. So just some function. Let's say sine t or something else. I mean, it doesn't actually matter, right? Some solution. I will just draw it graphically. For example, solution looks like this. And you want to stabilize it. So you want all solutions that start from different points to go and to join the solution over time. Okay? So you want to stabilize your solution. Arbitrary solution now, not constant. That is something we haven't done before. That is something that looks very much different from what we are used to looking at. Okay? Good. How do we do it? Well, the first step is to look at our equation. On the slides, it's equation 11. Here, it's equation on the blackboard. So this equation allows us to plug our solution there, like this. We just put stars here. So we say x star dot equals to a x star plus b, and here it's supposed to be some u. I'll call it u star as well. That makes it into a equality, right? That's the first step. That is what happens here. That is what provides the solution. So this x dot equals to ax star plus bu star. We know that this is equality. Okay, that's the first step. We just analyze, since we have a solution already, we should use it. We should use it in our discussion. First step. Second step. We can actually solve for u. And let me show you. How do we solve for u here? Well, it's very easy. We say that u is equal to b pseudo inverse times x dot star minus ax star. And that's it. So now you can ask me, that is cool, you know, but first, what if the solution is not a single solution? And second, what if the solution doesn't exist? So, does any of you, or all of you, had a discussion of pseudo inverses before? Do you know what pseudo inverse is? Pseudo inverse is a solution for least squares problem, right? That is the one way to introduce it.
I think also it's inverse that works only for one from the one side, so not the.
In a sense, yeah,
Like
yeah.
Inverse who works in both directions, so b minus 1b or b minus 1.
That picture of pseudo inverse is interesting, but we're not going to use it, and I will tell you why. We're only going to use pseudo inverse in the context of a vector multiplication. So we're not going to use it in the context of matrix multiplication. The reason is when you have a vector like this, b times vector equals to stuff, right? And we want to solve for, and we want to solve for this vector that was multiplied by b, in this case u, right? In this case, it is a least square problem. If you have a matrix multiply, it is a series of least squares problem. And I don't want to go there. It's just, extra level of difficulty of discussing, especially left and right, because it's just two sets of least squares problems, one on the left, another on the right. So, but good that you know that it is not, you shouldn't assume that it works same as inverse. Great. Now, let me give you a main piece of information about pseudo-inverse that you have to keep in mind. First, it doesn't have to provide zero residual solution. So what do I mean? I mean, if you take the solution that I drawn on the blackboard, which is equation 13, if you can see anything, probably not, this solution, and you plug it into our equation where it comes from, into, x dot equals to ax plus bu, doesn't have to provide you zero, equality. Doesn't have to. Pseudo-inverse. In general, unlike inverse. Inverse always provides you a solution. Pseudo-inverse can provide you closest approximation of the solution, or mathematical terminology, smallest residual solution. Okay? Smallest residual solution. Is that a residual? It's like a remainder. Let me put it. A residual is the, let's say we have a, how should I put it best? Let's say we have 7 and 1 here, and should be equal to a times 1 and 0. What can a be to make sure that it is as close to this? So, okay, now we'll define error as 7 and 1 minus a times 0 and 1. How do we minimize this error? Well, we can choose a equal to 7, right? If a is equal to 7, then your error is just 1 and 0, right? So this error is called residual, and this is the smallest residual solution. That probably is a more nice. Smallest doesn't feel like a mathematical term. least residual solution, probably called. But anyway, that is what we call residual, the error. And if you solved it exactly, it would have been exact solution, zero residual. But it doesn't have to be. Pseudo-inverse doesn't guarantee you zero residual solutions. It guarantees you least residual solutions. Okay, good. Now, what we get is this equation, which guarantees us least residual solution, but that is not satisfactory. We don't care about least residual solutions. What we care about is exact solutions. But in this case, we can guarantee it. We can guarantee exact solution, even though I've written pseudo-inverse. Why? Well, because if B did not span this x dot minus ax, if it didn't span it, this equation that was that is the equation where we plugged in our x star won't hold, and we know it does hold. We know that the x star is a solution to the original system. Therefore, equation x dot equals to ax plus bu, O stars, holds. And therefore, B spans x dot minus ax. And therefore, pseudo-inverse in this case provides us exact solution. Does this argument make sense? This argument is actually, interesting, more or less for control theory, but much more interesting, I think, for you as people who work in with data. Because here, matrices that I used here have to do with control, but they could have to do with anything else. It's just solution of differential equations. And what I said to you is, what I argued basically is that we can find exact solution for u, given that we have a x that satisfies differential equation. That style of argument goes again and again and again for different scenarios. So the style of argument, I think, is what you can try to take as your own. Is pretty good. All right. So in this case, it holds exactly. So you can find u star. Now, next step, we will define error. We will define error as x minus x star. Okay. Good. That is called control error, and we are going to use it again and again and again. So please pay attention to it. And next step after we define an error is to subtract from original equation our equation on the blackboard, or our what we call it, equation on the slides, x dot star equals to x star plus b. We just subtract one from the other. Seems arbitrary, but since both of them are exact equalities, it doesn't change anything, right? So you remember this trick from probably school time algebra, right? There people like to subtract stuff from one equation to the other. I think Gaussian elimination process likes this style of argument. I mean, so hope it is not something that makes you wonder why I'm doing it. All right, and after you subtract, just look into it. Left-hand side is e dot, error dot, because by definition, error is x minus x star. Next, we have a times error. And the last part, let me write it down for you. It is also, you cannot see it still because of the sun. So let me write it for you. So we have E equals to A plus, here you will have BU minus BU star, right? So let me define V as U minus U star. Just a control error, basically a divergence from our desired control. So how far we are from our desired control? V is equal to U minus U star. Okay, sounds fair enough. Now we have a new equation. you can see this equation number 17 on the bottom of the slide. Can someone tell me how to deal with this equation? I want it to be stable. Yeah, so exactly. So you just find v equals to minus ke. Substitute it into our equation. It will give you you will find k such as a minus bk is stable, and that's it. Except your control input was u, not v, right? So substitute instead of e x minus x star, and instead of v u minus u star. Yes. Yeah, we converge to solution. Yeah, u star is the control input that would drive us along the solution x star. So if our initial conditions were exactly the same as for initial conditions for x star, then u star would be the control input that we would need to put into our control system or into this equation. This would drive it along this trajectory. Yeah, so there's some is the control that we want to apply. You can see that u, in this case, has two components, right? And u star is just one of the components. And if we have zero error, u star is the only component. You'll see it on the next slide, where I think, discuss it, exactly this question that you raised. So in control system, now time for terminology, and I would suggest, again, spike of attention. Control terminology. We often break down our control into two parts: feedback control and feed-forward control. Feedback control is stuff like minus x times x minus x star, stuff like this. Basically, it is something that requires feedback, so sensory information, okay? Feed-forward control is stuff that does not require it. When I say does not, it is not a clear division. For example, here, you can see that if you open the brackets, minus k times x star will not require state information. X star is given function of time. So in fact, this is arbitrary. I just decided to put those brackets in. I didn't have to, but it makes a lot of sense because what you care about is the error, not necessarily x. And error requires x. But since terminology is arbitrary, don't pay too much attention to it. So for example, I call this state feedback, but you can decide to call only minus kx feedback control. Up to you. And in some contexts, that is what happens. In some contexts, but it is not very often. Feed-forward part is much more clearly defined. Feed-forward part is something that does not contain x. So you cannot call something that contains x a feed-forward part. There is a big reason for this division. And the reason is that feed-forward often depends on the solution that you want to obtain. And you have to design it going from your solution. If you already know where you want to go, feed-forward comes automatically. Feedback, on the other hand, depends only on your dynamics. So you don't have to know where you want to go to obtain it. For example, K matrix in this context depends only on two variables, A and B. As long as you know your dynamics, you know your K, you can know your K. Just solve for A minus BK having negative eigenvalues, and you get your K. You don't need to know anything about your trajectory, right? That is a good thing about division. You can solve those problems independently. And that is what people do in practice. So often enough, entire paper will be only about how to get K. or only about how to get U star. And maybe you find it strange because it is so simple here, but in real examples it's not simple. So real examples as in like walking robots, or as in some other hugely complicated system. Even quadrotors would be relatively trivial in this aspect, but we are not just working with quadrotors. So that is a division. That is terminology. Don't let it scare you, okay? It's just a terminology. It doesn't have profound meaning. Okay, good. By the way, I'm not sure if we already mentioned it, but when we plug in U into our system, we often call it closed loop, because we closed the loop, right? Because we have X as some sort of output, in our head at least, something that we want to control. And we put it as input to the system as minus kx. That is the picture that you can have. But or just remember, we call it closed loop. So when your system became autonomous again, as here, right? Autonomous system. But it is autonomous only because you chose your control already. That we call it closed loop. And you often come to discuss with people and they say, so do you talk about closed loop system or do you talk about your original system? And you should know that they ask, are you discussing this guy or are you discussing this guy? Okay, that is the terminology. But as same as most control terminology, you just it's like you need a dictionary pretty much, right? If you have a dictionary in your head, this is perfectly fine. It's not mathematical terminology when you need to also understand deep concepts. All right, let me see. How much time do we have? How much? 15? Okay. I actually have a whole lot more material, and I think we are a little bit behind the time. So let us do it this way. Ask your questions now, so we at least have time to answer. And then I will go as far as I can. How define what? So X star is supposed to be given to you. You want to stabilize a point, and you stabilize it, right? And you stabilize it. But did I just deliver the whole lecture without a microphone? Horrible. All right, now we will have an experiment of seeing how a microphone affects the quality. Sorry for the people on the back. I mean, I can hear myself, but I'm not sure if you were able to. Yes?
Usually when we talk about the system being stable, we talk about one particular initial condition.
No. When we talk about the system being stable, we usually talk about every initial condition near the solution. So you have one solution, but it's supposed to be stable for all initial conditions around the solution.
So we choose one solution.
Yeah, X star. Yes?
How to find U star?
Like this, for example, for this example. For this example, that is a way to do it. For previous example, it was different. For every example, it will be a different approach. That is pretty much what I want to continue on this. That's why I want. Okay, one more question.
Can you explain one more time why should reverse in this case gives one event solution?
Why should the reverse gives a class solution, right?
Yes.
Okay, so pseudo-inverse in this case, let me go back on the slides. Pseudo-inverse in this case gave exact solution because this equation here, like x dot star equals to ax star plus bu star, we know that it holds. Microphone stopped working? So we know that it holds, right? This equation x dot equals to ax plus bu has to hold because we know that x star is a solution. I think the microphone just doesn't have battery, so I apologize. But anyway, also, we since it holds, we know that ax plus x dot plus ax or minus ax has to be spanned by b, otherwise it won't hold. Oh, just that. All right, so let us go through the last few parts. Or should we just stop? Let me just think about it. I don't want to rush because the last parts are also very important. So let us do this. We'll pause here. Next time we'll go through the whole, because we still have like half of the material I want to cover yet. So we'll go next time through the rest of the material and we go without a hurry, but hopefully with less technical issues. But sorry about the microphones, really. It's pretty amazing how often they fail. But all right, thank you for your time today, and hope we'll be able to solve both technical problems and to improve your experience during the labs. Thank you.